Today, we're tackling a problem that challenges your understanding of bitwise operations. Given a sequence that's been XORed and the very first element, can you reconstruct the original sequence? It's a fundamental test of how well you can reverse engineer bitwise transformations. You're given an array called encoded, where encoded at index I is the result of XORing original at index I, with original at index I plus 1. You also get first, which is the very first element of the original array. Your task is to reconstruct and return the entire original array. The core challenge is leveraging the XOR property to unravel the sequence element by element. A straightforward approach might involve iteratively building our result list. We start by adding the given first element. Then, we loop through the encoded array. For each encoded value, we take the last element added to our result and XOR it with the current encoded value to find the next original element. We append this new element to our result list. This approach works by directly applying the XOR property at each step. It's not inefficient in terms of operations, but building a dynamic list and converting it to an array at the end might incur some overhead if the list reallocates frequently. Time complexity is linear, O of n, as we visit each encoded element once. Space complexity is also linear, O of n, for storing the result. The key insight here lies in the fundamental property of XOR. If a XOR B equals C, then a XOR C equals B, and B XOR C equals A. This means we can reverse the operation. Since encoded at index I is original at index I XOR, original at index I plus 1, we can deduce that original at index I plus 1 must be original at index I XOR encoded at index I. Knowing this, we can pre-allocate our result array to the correct size. Encoded length plus 1. We set the first element of our result to the given first value. Then, we iterate from the first element of the encoded array. In each step, we calculate the next original element by XORing the current original element with the current encoded element. We store this directly into our pre-allocated result array. This avoids the dynamic resizing of a list, ensuring efficient memory usage from the start. Let's trace this with encoded being 1, 2, 3, and first being 1. We initialize our result array of size 4 and set result at index 0 to 1. For the first iteration, I is 0. Result at index 1 becomes result at index 0 XOR encoded at index 0, which is 1 XOR 1 resulting in 0. So, result at index 1 is 0. Next, I is 1. Result at index 2 is result at index 1 XOR encoded at index 1, so 0 XOR 2, which gives us 2. Result at index 2 is now 2. Finally, I is 2. Result at index 3 is result at index 2 XOR encoded at index 2, which is 2 XOR 3, giving us 1. Result at index 3 is 1. The loop finishes and we have our complete original array. The final reconstructed array is 1, 0, 2, 1. This is correct because by applying the XOR property iteratively, we've successfully reversed the encoding process to reveal the original sequence. You'll spot this pattern whenever you need to reconstruct a sequence where each element is defined by a relationship with its immediate predecessor, especially when that relationship is a reversible bitwise operation like XOR. Another cue is when you're given an initial value and a series of transformations to apply sequentially. Time complexity is O of n, as we perform a constant number of operations for each element in the encoded array. Space complexity is O of n, for storing the reconstructed original array. This problem highlights the utility of XOR's inverse property. Try the next problem to see if you can apply this same pattern. Don't forget to like and subscribe for more DSA insights.